Hope everyone's doing well. Today, we're going to discuss the central limit theorem. Probably no one knows what the central limit theorem is, but I'll try to do my best to demonstrate it. Suppose I have a single die. Here I'm rolling. You can't see that, but I got a single die. I roll it a whole bunch of times. What do you expect the outcome to look like? Well, we're going to get number 1 sometimes. Sometimes we get 2, 3, 4, 5, and 6. Those values we'll get. I think everyone's okay with that. Now, how many times will we get these numbers? Well, we should get them all about the same amount of time. Distribution should look a lot like that. It should be very rectangular in shape. Clearly, well, actually, this has a name. This is actually a uniform distribution. That is a uniform distribution. Now, let me show you what happens. I'm going to take 2 dice. Got a green one and a white one. Roll them up. How many ways are there to get this such that the average of the dice, the average, equals 1? 1 plus 1 divided by 2. That's 2 divided by 2. That's an average of a 1. Now, what happens if I had a 1 and a 3? 1 plus 3 is 4. 4 divided by 2 dice is a 2. The average of that is a 2. What about if I had 1 plus 5? 1 plus 5 is 6. 6 divided by 2 dice is 3. So what's going to happen is the average of these dice. Okay, here we have n equals 1 die. 1, 2, 3, 4, 5, 6. Here we have 2 dice. 1 can only happen one way. 3 happens 3 times as often. Wait, let me make sure I get that right. 2 happens 3 times as much as 1. 3 happens 5 times as much as 1. And this is a symmetric situation. Okay, so that's what the distribution would look like if we found the mean of 2 dice. All the different possibilities. Now, this would look like a triangle. The shape of the distribution has changed. It was flat on top. Now it's a triangle. What if we do 3 dice? There's still only one way to get an average of 1. There's only one way to get an average of 6. They all have 3 have to be 6 to get an average of 6. But what's going to happen here, let's go n equals 3. What's going to happen, 1, I'm going to try to line this up. That still can only happen one time. That still can happen only one time. But we have more dice. That means this is going to happen more than 5 times as much than this. 3 will happen more than 5 times as much as 1. 2 will be a little bit more than 3. But what's going to happen? This thing's going to start to curve. Here we had a nice rectangle. Here we have a nice firm edged triangle. Here, it's starting to smooth out a little bit. It's getting a little bit of a curve in it. Now, unfortunately, I got to move over here because I'm out of space. But what's going to happen? 1, 2, 3, 4, 5, 6. What's going to happen when I have even more dice? Here I have a handful. There's still only one way for that average to be 1, and that is if every one of them is 1. There's still only one way for the average to be 6. That's if they're all 6. But to get an average of 3 or an average of 4 or average 3.5, this happens a whole bunch. What happens, we get something like this. It curves out real nicely, and n is big. We just call it big. When n is big, something happens to this particular distribution. It becomes normal. The distribution becomes normal when n is big. Now, how big is big enough? Big enough is greater than 30. So when n gets bigger than 30, when your sample size is bigger than 30, the sampling distribution of all these sample sizes will be normal. The original data set was not normal. The original data set in this case was uniform. Then it became triangular. But when n was big enough, that sample size was big enough, it transformed into a normal distribution. This is going to make us be able to turn any problem we want to into a form of normal problem that we can use to predict things. Now, what I'm going to do is I'm going to stop you for a moment, and I am going to summarize this. Okay, I'm back, and I have summarized the central limit theorem. Okay, so let's read this. As the sample size n increases, as I demonstrated with my dice, with that limit, n gets bigger and bigger and bigger forever. The shape of the sample means, these are sample means, not the original data, taken with replacement from a population with the mean of the population's mu and the mean of the standard deviation of the standard deviation of the population sigma will approach a normal distribution. So all this is saying is as our sample size gets bigger and bigger and bigger, our new distribution, our sampling distribution of all those samples of dice will look normal. Now, this sampling distribution that we've created will have the mean mu. It's going to have the same mu, same mean as the original population. Well, if you remember seeing that, we had that one, then we had a triangle, and then we get around, and the mean was the same all the way, all the time. The mean stays the same, which is a very nice thing. And the standard deviation becomes sigma over the square root of n. That's quite nice because the standard deviation could be a real difficult equation, but it's just square root of sample size. That's it. They just take the original standard deviation divided by square root of sample size, and that's your standard deviation of the sampling distribution. In addition, we can assume the sampling distribution is normal if the population is normal. Okay, if this central limit theorem, what it does is it takes something and it becomes normal. But if it's something's already normal, then it won't get more normal. It's already normal. Or n is bigger than 30. N is big enough, like I said earlier. Now, you may want to say, what in the world is going on? Well, we did have this equation with a normal distribution. Well, what we have now with our sampling distribution, it has the same mean as this one, which is the same as the mean of the population. And sigma changes to this. This equation becomes this for the central limit theorem. So, what's your question? When do I use this? When do I use this? Use this one. And I'll tell you why. I don't know whether you noticed, but all those other problems where we use this, we chose an individual bottle, or an individual football. There's always a 1. Here, our sample is going to have a size. N is going to be bigger than 1. But what if you plugged in 1 here? What's the square root of 1? 1. Anything divided by 1, that equation becomes that when n is 1. So if you always use this equation, you'll always be right. When n is 1, this situation works, but it'll work there too. You plug in 1 and you get that equation. When n is something other than 1, you can't use this. You have to use this. Well, it works here, 2, 3, whatever n is. So this is the equation you're going to need to know for the rest of the course. And that's the central limit theorem. Next thing we'll do, I'm going to sign out. Next thing we'll do is some examples.